Section 6.6, the convolution integral. So sometimes when we're solving a differential equation using the Laplace transform method, um, towards the end, suppose that we arrive at a situation like this. So the Laplace transform of y, which is y is what we're looking for, right? Y is the solution of our differential equation. Towards the end, let's say at some point we get Laplace transform of y equals something. Let's say h of s. So some expression in terms of s here, some function of s. And we would like to invert this to figure out what y is, right? Because y would be, if we arrive to this situation, y would be the Laplace inverse by taking the Laplace inverse on both sides. Y would be the Laplace inverse of h. And to have a concrete description of y, we need to invert this. So sometimes it's hard, but sometimes we can split h into a product of two functions. So sometimes we might recognize that h is perhaps, let's say, f of s times g of s, where this one we can invert, and that one you can invert. So perhaps looking at it at this one, it is not obvious how to invert it, but you might be able to express or factor h into the product of two other functions, each of which you can invert. And the hope is that, well, I can invert that, and I know how to invert to this one. Can I somehow, knowing the Laplace inverse of each of these, can I somehow put them together to get the inverse of h? And the answer is yes, but it's not the obvious way of. It's not the obvious way. So the Laplace transform of h of s, which, because h of s is equal to this, will be the Laplace transform of f of s times g of s. But it turns out that it is not so simple as just saying the Laplace inverse of f times the Laplace inverse of g. That is not true. So the story is a little bit more complicated, or pun intended, convoluted than that. So we introduce then notation, a concept that allows us to describe how to find the Laplace inverse of a product using the Laplace inverse of each of these pieces. So how do you put them together to get the Laplace inverse of h? So that is by means of the convolution integral. So what is a convolution integral? So suppose you have two functions, f and g, both defined on the non-negative real numbers, so positives and 0. And suppose that those two functions are integrable. So you can find the integrals over any closed interval. Then the convolution integral of f and g, and we use this notation f star g. So the star is like a sort of product, but we specifically do not use a dot because that would be just the usual product. We use a star. So f star g, and you can rate that f convolved with g, or you can just say f star g. It is defined by this. F convolved with g evaluated at t is going to be the integral from 0 to t of f of t minus tau. That is the Greek letter for t, tau. So big, when you write it big, that looks like that, tau. So the integral from 0 to t of f of t minus tau times g of tau d tau. So that means we're integrating this function with respect to tau. Tau is our variable, and for the purpose of the integral, t is a constant. Of course, once you compute that integral, the tau is a dummy variable, so you end up with an expression only in terms of t, so t becomes a variable for the function f convolved with g. This integral is inspired by how you multiply polynomials or series. Therefore, in a sense, the convolution integral is a type of product, hence a notation. So when you think of the product of two polynomials or the product of two series or power series, that would be like the discrete case, and then the integral would be the continuous case. All right, so here are the properties of the convolution integral, and all these properties follow rather easily from the properties of the integral or from some other simple trick like the U substitution. So they're all really easy. You can figure them out on your own. I'm not gonna prove them, but again, there's nothing really hard or mysterious or difficult about deriving these properties, showing why they're true. The first one, for example, follows just by a U substitution, and the third one follows by using the linearity of the line of the integral. So they're very easy to figure out that they're true. Okay, so here are the properties. The very first one says that the order in which you compute a convolution integral does not matter. So the convolution integral or convolution product is commutative. So f convolved with g is the same as g convolved with f. The second one says that you can move parentheses around. So if you had three things, convolving the first two and then convolving with the third would be the same as if you take the last two first, do that, and then convolved with g. So you can regroup. That's the associativity property. You can also distribute over additions, over sums. So f convolved with g1 plus g2 would be the same as f convolved with g1 plus f convolved with g2. And lastly, and this is the main property, would be that if you find the Laplace transform of a convolution product, then that is the Laplace transform, the product of the Laplace transform. So this, if you had if you were trying to find the Laplace transform of two functions being multiplied together, that is not equal to the Laplace transform of f times the Laplace transform of g. That is not true. However, if this product right here, which is just a regular product, were replaced with a convolution product, then it would be this. Then this thing right here would be true. The Laplace transform of f convolved with g, or you can just use this notation, f convolved with g evaluated at t. This will be the product of the Laplace transforms. So the Laplace transform of the convolution product is the product of the Laplace transform, but it is not true for regular product. And similarly, the Laplace transform of, so suppose like I'm trying to invert Laplace transform. If I have that, I can write the thing that I'm trying to invert as a product of two functions, then the Laplace inverse of that product is not the product of the little f and gf and the little g, but the convolution product of the little f and the little g. In other words, using Laplace transform notation for this, for both sides here as well, just like I did here, it would be the Laplace transform of f s g s is equal to Laplace transform inverse. The Laplace transform inverse of the product is the Laplace transform inverse of f convolved convolution product Laplace transform inverse of g. So it's not is regular product, is convolution product. Let's work on the first example. It says find the inverse Laplace transform of h of s, where h of s equals a over s squared times s squared plus a squared. A is a constant that could be any number. It's not a variable. The variable is s. So we want to invert this. Now, the idea is, of course, this is not on the table of Laplace inverses that we have. However, the strategy is, even though that is not in the table of Laplace transform, we can rewrite this and split it up a little bit and write it as a product. This is the product of two things, each of which is in the table of Laplace transform. So we wrote that as a product of two things for which we can figure out the Laplace transform easily or independently. So the first one, this one is number 3 on the table, on our table, and then this one is number 5. So we don't know the Laplace inverse of this, but we were able to write the function h as a product of two functions, each of which we can easily find out was the Laplace transform, the inverse Laplace transform. So that means then the inverse Laplace transform of h is equal to, okay, now I'm going to copy this because h is equal to that. We're looking for the Laplace inverse, this product right here. And this is the Laplace inverse. So the Laplace inverse of the product is the product of the Laplace inverses, but not the regular product, the convolution product. So this is going to be 1 over s squared, Laplace inverse of 1 over s squared, product, convolution product, Laplace inverse of a over s squared plus a squared. Okay, now looking this up again, that's number 3, that's number 5. The Laplace inverse of 1 over s squared is t. The Laplace inverse of a over s squared plus a squared is sine of a t. So now we found what is the Laplace inverse of h. But we're not going to leave it like this because we have a formula for what that is, so we can actually keep going and figure out, nail exactly what is the Laplace inverse of h. Right, so according to the definition of what that is, the definition of the convolution integral, convolution product, it is going to be then the integral from 0 to t. So this is the integral from 0 to t of the first function, evaluated not at t but at t minus tau, and then the second function evaluated at tau. So the first function, which is just the identity function t, evaluated not at t but at t minus tau, so this is going to be t minus tau, times the second function evaluated at tau. So second function is evaluated instead of at t, at tau, and then d tau. All right, now let's compute that integral. And I'm going to start a little bit further to the left. All right, this is going to be, we can distribute here, so t times sine of a tau minus tau sine of a tau. So distribute this over here. So this is going to be the integral from 0 to t of t sine of a tau minus tau sine of a tau d tau. Okay, so just distributing that, this times this minus that times that, you get this. And now, using the linearity property of the integral, this is the integral of the difference is the difference of the integral. So this is the integral from 0 to t of t sine of a tau d tau minus the integral from 0 to t of tau sine of a tau d tau. All right, now in this integral right here, I'm integrating with respect to tau. So tau is a variable, so that means everything else is a constant for the purpose of computing the integral. So that means that t in particular is also a constant for this purpose of the integral. So that means I can pull it out because it's a constant, okay? So for the purpose of the integral, is a constant. So this is t integral from 0 to t, pulling it out, sine of a tau d tau minus integral from 0 to t of tau sine of a tau d tau. Okay, now this integral right here, you can either do in your head or do a u sub where the u is just the inside of the sign, so u would be a tau. But if not, you can do it in your head. This one is not a difficult one. So I have this t right here, and then this one, the integral of sine is negative cosine, so this is going to be negative cosine. But then you have to divide by a. So this is going to be negative 1 over a cosine of a tau. And then you're going to plug in between 0 and t. So you plug in, you're going to plug in 0 and t. So that's an integral. So that was a u sub, or just do it in your head. And then this one is an integration by parts. And so I'm just going to skip the details. You know how to do integration by parts. Even if you forgot, review that at some point during the class. You can practice that if you want to. I'm just going to skip the details, and you get, if you do integration by parts here, this is negative tau over a cosine of a tau plus 1 over a sine of a tau, and you plug in tau equals 0, tau equals t. So you evaluate it between 0 and t. Okay, now let's plug in and then simplify. If you plug in tau equals t, this one is going to become, I'm just going to put these two together. So this is minus t over a cosine, and I'm plugging in tau equals t, so this is a t. Then minus, and then there's this minus, so this is actually going to be a plus when I simplify. So minus, and then plug in tau equals 0 here, you get this minus. Then this is t over a cosine of 0, which is 1. So just, I don't write that. That's just a 1. Now, that's done. Now here, plug in tau equals t. So plugging in tau equals t, you're going to get negative t over a cosine of a t plus 1 over a sine of a t. Okay, so this first bracket is what you get when you plug in tau equals t minus, and now let's plug in tau equals 0. When you plug in tau equals 0 here, that becomes a 0, and then cosine of 0. So, but because you multiply 0 times this is going to become 0. The first term becomes 0 when you plug in tau equals 0. And then the second term, when you plug in tau equals 0, well, this will become sine of 0, which is 0. So that is also 0. All right. And then now let's continue simplifying. This is going to be this one. Well, there's nothing to simplify in this one. Negative t over a cosine of a t minus a minus becomes a plus, so plus t over a. And then, well, that one, that is 0, so I can ignore that part. Minus and minus becomes plus. This is t over a cosine of a t. And then this minus and that plus becomes a minus. Minus 1 over a sine of a t. And then note that the first term and the third term are identical but with opposite signs. So that means they're going to cancel each other. They cancel each other off. So the only thing that survives is the second term and the third and the fourth term. So the answer to this is t over a minus 1 over a sine of a t. And that right there is what we were looking for. The Laplace inverse of h evaluated at t is t over a minus 1 over a sine of at. Here's a different example. It says find the Laplace transform of h of t where age h equals the interval from 0 to t of t minus tau squared cosine of 2 tau d tau. Alright, that integral right there should remind you, because it looks a lot like the convolution product of two functions. So what is the convolution product of two functions? This is the integral from 0 to t of f t minus tau g of tau d tau. A direct comparison shows that indeed, I mean, this has exactly the same form. So in fact, this is a convolution product. It is a convolution product of what? Well, it is a convolution product of these two functions. I'm going to write in a second. So let's rewrite this. So this is h of t is, I'm just going to copy this for convenience. So this is t minus tau squared cosine of 2 tau d tau. Making the direct comparison, right there you see that f must be the squaring function and the g must be the cosine of a double angle. So, so this is, if I let me use another color. Do I have another color? No, I guess not. if I let f of t be the squaring function, and we let g be the cosine of double angle, so make it, noticing this is going to be then, we can rewrite this integral as the integral of from 0 to t of f evaluated at t minus tau, g of tau d tau. So you see, this integral was in fact, is in fact, the convolution integral or the convolution product of two functions, these two functions. So that means this is f star g, f convolved with g evaluated at t. So h of t is f convolved with g evaluated at t. So h is the convolution product of f and g. So then that makes things simpler, because then if I'm looking for the Laplace transform of h, then that is the Laplace transform of f convolved with g evaluated at t, which is then the product of the Laplace transform. So this is the product of the Laplace transform of f times the product, times the Laplace transform of g. Now, f of t is t squared, right there. F of t equals t squared, and g of t equals cosine of 2t, so let's replace those things. So, Laplace transform of t squared times Laplace transform of cosine of 2t. And then you look these up in the table of Laplace transforms. This is 3 and 6. These will be 2 over s cubed times s over s squared plus 4. Which you can simplify by just writing it as a single quotient or rational expression. This on top you have 2s over, so multiplying across basically, over s cubed, s squared plus 4, and you can cancel an s, one s from the top, one from the bottom, and you end up with 2 over s squared plus 4. Example 3. In this example, we're going to actually solve an initial value problem. And in this example, when we solve this differential equation using the Laplace transform method, we're going to run into a spot where we're going to need the convolution product, and we're going to then give the final answer in terms of a convolution integral. We're not going to be able to give an explicit solution, because we don't really have an explicit formula for g. We don't know what g is. G is just an arbitrary function. So we're going to leave then the final answer in terms of a convolution integral in terms of g. Alright, so let's start by, as usual, taking the L, because we're going to be using the Laplace transform method. Take the Laplace transform on both sides. So I'm going to put Laplace transform on both sides. And using the linearity of the Laplace transform right away, we can write it like this. So it's going to be the Laplace transform of y double prime plus 4 times Laplace transform of y prime plus 4 times Laplace transform of y equals the Laplace transform of g. Of g. Now, using the formula for the Laplace transform of the second derivative, this is, and I'm going to put it in brackets, this is s squared Laplace transform of y minus s y at 0 minus y prime at 0. Okay, that is the Laplace transform of the second derivative, plus 4. Now we use the formula for the Laplace transform of the first derivative. So this is a Laplace transform of, sorry, I forgot the s. And yeah, I forgot one s here. So s, Laplace transform of y, minus y of 0, plus 4, Laplace transform of y, equals Laplace transform of g. Okay, and now we plug in what this is. These are the initial conditions. So we know what that is, and we know what that is, and we know what that is. So now we just plug in 2 and negative 3 where appropriate. So this is going to be s squared Laplace transform of y minus y at 0 is 2, so this is going to be minus 2s, minus the y prime at 0 is negative 3, so this is going to be minus negative 3, minus and minus, minus and negative is a positive, so plus 3, plus 4, s, Laplace transform of y, and then y at 0 is 2, so this is going to be minus 2, plus 4, Laplace transform of y, equals Laplace transform of g of t. Okay, now we're going to, we have to distribute this 4 over here. So let's start distributing. I don't need these brackets anymore. I only put the brackets to distinguish that this whole thing inside the brackets was the Laplace transform of y prime. So I'm going to write y, s squared Laplace transform of y minus 2s plus 3. And then distributing this is 4s Laplace transform of y. And then 4 times minus 2 would be minus 8 plus 4 Laplace transform of y equals Laplace transform of g of t. Okay, now everything that doesn't have the L, we're trying to solve for the Laplace transform of y. Everything that doesn't have the L of y is going to move to the other side, and everything that has the L of y is going to stay on this side, on the left hand side. So then you're going to have s squared Laplace transform of y plus 4s Laplace transform of y plus 4 Laplace transform of y equals Laplace transform of g of t, and then I can combine this 3 and that negative 8, so that's negative 5. Negative 5, when you move to the other side, is going to be plus 5, and then these negative 2s uh, becomes positive 2s. So this is 2s plus 5. Alright, and now factoring out the Laplace transform of y, because it's a common term for all of these, this is going to be s squared plus 4s plus 4 Laplace transform of y equals Laplace transform of g of t plus 2s plus 5. Okay, now we divide by this and we get the Laplace transform of y. So this gives us then Laplace transform of y equals, and then I have Laplace transform of g of t, and then it's supposed to be over s squared plus 4s plus 4, but instead of writing all that over, I'm going to write it as times 1 over, write it as a product, s squared plus 4s plus 4. Okay, and then this over the same thing. So 2s plus 5 over s squared plus 4s plus 4. All right, now we're going to factor that, and this is Laplace transform of g of t. Factoring that, this is 1 over s plus 2 squared, and then this is 2s plus 5 over s plus 2 squared. Okay, all right. Now it's time to invert, so we can figure out what y is. Y is just the Laplace inverse of that. Y is just the Laplace inverse of that. Now, the Laplace inverse of this is a product, so the Laplace inverse of this is just going to be the convolution of the Laplace inverse of this one, which is g, times the Laplace inverse of this one. And the Laplace inverse of this one, well, this is just a rational function, so we can use the methods we have learned before to tackle it. So, all right, so now inverting, we're going to get that. So I'm going to write down what I just said. Inverting, this is the Laplace transform, the Laplace inverse of this. The Laplace inverse of that is g of t. Convolution product, the Laplace inverse of this. Laplace inverse of that. Okay? Again, the Laplace inverse of this product is the convolution product of the Laplace inverses. That is the formula that we're learning in this lesson. Plus Laplace inverse of 2s plus 5 over s plus 2 squared. So that is y. Now, let's do these two inverses. This is the only thing, we can do that one and that one. This is on the table. This is actually going to be number 11 on the table. This is going to be number 11 on the table using a equals -2 and n equals 1 in that formula. So we can figure that one out. And this one, though, that is a rational expression. We know how to tackle that one. It's not on the table, so we have to do its partial fractions. Now, if you write this in, if you split that up into its partial fractions, and I'm going to skip that because I've already done plenty of partial fractions, and you know how to do this. If you do the partial fractions to this, this is 2 over s plus 2 plus 1 over s plus 2 squared. Okay, so that is the partial fraction decomposition for that. So that means to find the Laplace inverse of this is just the Laplace inverse of that plus the Laplace inverse of this. So that means that y is going to be g of t convolved with Laplace inverse of 1 over s plus 2 squared plus, instead of Laplace inverse of that is just Laplace inverse of this plus Laplace inverse of that. So this is plus Laplace inverse of 2 over s plus 2 plus Laplace inverse of 1 over s plus 2 squared. Okay, now when we look this up in the table of Laplace transforms, you're going to find that this is number 2, but we have to pull out the 2 from there, because if you look at the table for number 2, there is a 1 at the top. So we have to factor out the 2 out of there, and then we would have 1 over s plus 2, and that would be this, where a equals negative 2. It will be this where a equals negative 2. Okay, so that means that will take care of that. And how about this one? This one would be number 11. It would be this one where n equals 1. We have a 1 in there on the top. And the exponent is 2. So again, with n equals 1, that works. And the a equals negative 2. So that means we really can take care of both of these now. So let's write down the answer. We're going to probably be a few more steps. So this is going to be equal, so y equals g of t convolved with, and using, well, let me write that here. This one is going to be, I already wrote it over there. Again, is this number 11 with a equals negative 2 and 1, which is this one as well. So that is t e to the negative 2t. Number 11, when n equals 1 is t, and then a equals negative 2, a to the negative 2t, plus that one, we have to pull out the 2, so 2 Laplace inverse of 1 over s plus 2, plus this one is that one, t e to the negative 2t, which equals, so almost done, so this is going to be g of t convolved with t e to the negative 2t plus um, that one is number 2 with a equals negative 2. So this one is number 2 with a equals negative 2. This gives me 2 times e to the negative 2t plus t e to the negative 2t. Okay, so that is um, an explicit formula. We could simplify it, we could leave it like that, but actually the instructions are a little bit more specific than that. It says write the answer in terms of a convolution integral. So that means I want to leave it in terms of an integral. So I want to write down what this is explicitly, what this convolution is explicitly in terms of an integral. So that means we're going to write the answer as this is the integral from 0 to t of g t minus tau tau, so it is the first one at t minus tau and the second one at tau. So this one, instead of at t, is at tau. So tau e to the negative 2 tau d tau plus 2 e to the negative 2t plus t e to the negative t. So you could then leave it like this. Okay, or if you wanted, you could factor out the e to the minus 2t from there. So the last version that you could offer as your final answer could be um, this. I'm just rewriting this part. Plus factoring out the e to the minus 2t, you get 2 plus t, or just t plus 2. So t plus 2, or 2 plus t, same thing, e to the negative 2t. So that could be the last version you could give as your final answer.